All right, welcome everyone, and good afternoon, and welcome to the second edition of the Nothing Stands Still Challenge to be presented here at the Future of Construction workshop at ICRA. My name is Julian Kindle, and I'm a robotics engineer at Hilti, as well as industrial PhD student at the Robotic Systems Lab at ETH Zurich. And on behalf of the challenge team, I will be presenting to you, or quickly give you a short overview about what the Nothing Stands Still Challenge is about, how it has changed from last year's challenge, and we will be announcing the winning teams today. Maybe first of all, why is the Nothing Stands Still Challenge, or why is the Nothing Stands Still Challenge of interest to the company which I'm representing today, Hilti. So Hilti is a innovation-driven company, and we've already seen it in previous presentations today that we have this one robot out in the market, which is the Hilti J-Bot, which is a semi-autonomous drilling robot for ceiling drilling applications. And for Hilti, the Nothing Stands Still Challenge is of relevance when it comes to reality capturing. So not only providing a customer the ability to create a 3D scan of an environment or of a construction site, but also understand what has happened and document what has happened throughout the construction process. Now, for those of you who are not familiar with the challenge, the Nothing Stands Still Challenge is a joint effort between Iro Armeni, Tao Sun, and Emily Steiner from the Gradient Spaces Lab at Stanford University, as well as Michael Hillenberger and Torben Gräber from Hilti's corporate research. And the idea of the Nothing Stands Still Challenge essentially is to bring the development of methods forward which focus on the reconstruction of 3D point clouds, or more specifically 4D point clouds. 3D point clouds with a temporal part of it, so basically spatio-temporal point clouds. And an example of that you're actually able to see here on this slide. And with state-of-the-art, basically in literature, most focus in recent years was put on to point cloud registration in static environments. So basically when nothing has changed, for example, with methods like ICP, etc. However, these methods fail in environments where you have a lot of change throughout the process, or throughout the point clouds which you would like to match against each other, which is especially the case in construction. Now, why do we at all want to build spatio-temporal maps of construction sites? So construction is one of the most wasteful and inefficient industries which is out there, with about 50% of the addition or of costs when it comes to of additional costs of construction projects being due to rework. 20% of all occupational fatalities happening to construction workers, and most of the non-hazardous materials used on construction site, which would be recyclable, are actually just being dropped into landfills. And building spatio-temporal maps is one of the first steps when it comes to tackle these problems with, for instance, knowing or documenting why rework has been done for specific parts, and therefore preventing it in the future, detecting dangerous environments or dangerous scenes for construction workers before a fatal accident happens, as well as documenting which materials have been used where on a construction site, so that in the far future, when the building is deconstructed, we actually know which materials have been used where and can properly sort that out. Now, the data set of the Nothing Stands Still Challenge essentially followed 6 distinct construction sites. And basically, if you think about a construction site, the building process is quite long. You start with nothing and end up with a completely ended building. And specifically where the Nothing Stands Still Challenge has focused on is on the interior layout process. So basically, we start off with a building which is already present with outer walls as well as columns, etc. But otherwise, it's an empty building. And then the whole interior structure is added, such as electrical installations, drywalling, brick walling, ventilation, etc. And I'm not going in, or basically, whenever a in these 6 construction sites right before a major construction step has happened. So for instance, installation of a wall, which would have occluded parts of the data set. A new data set was recorded so that we end up with multiple stages for each construction site for the data set. And I'm not going into too much detail for the challenge, but rather I'm referring to the ICRA submission called Nothing Stands Still by Tao Sun et al. For the interested reader to get more information about it. Now, in the following, I'll be giving you a couple of examples why we are interested in having spatio-temporal representations of environments. Now, what you can see here is basically the same construction site, a mesh of the same construction site, just captured with a couple of months in between. And as you can already see, the blue or green one, I think it's blue on screen. The blue one is basically empty, while the yellow one is quite filled. And what a fact which many people don't know is that when we look at a building, most of the walls are actually not made out of concrete. Like pouring of the concrete is actually only happening for structurally important walls, so which are needed in order to support structure as well as pillars. So what you can see here is that we are actually starting off with a completely empty room and only then add the inner structure, like inner walls, to the building through processes like drywalling or bricklaying, etc., which of course drastically changes the appearance of the construction site when we talk about recording a point cloud, for instance. Now, this process also requires a lot of material, which is usually stored on site. And of course, that also significantly changes the appearance of the construction site. Now, one of the worst cases probably is if you think about that a certain pile of material, let it be bricks, being stored at a certain location on a construction site, the bricks are all being used and the next pallet of bricks is positioned there. Suddenly you have this dynamic part in your data set where basically these objects are only moved by a couple of centimeters or a couple of tens of centimeters, which makes detecting outliers, for instance, quite challenging. And similarly, if you think about installation of these drywalls, what you usually do is you create a framework, then you fill that with insulation, and ultimately you don't want to be able to see the insulation, but rather you cover it up. So if you record a data set right before, like when insulation was present, and then after installing wall panels, suddenly your data set or your point cloud for that specific wall is shifted by only a couple of centimeters, which makes registration, of course, quite challenging. Now, the Nothing Stands Still challenge has, as said, recorded data sets of full construction sites. So basically what the team did is they used these off-the-shelf 3D scanners, in that case a Matterport 3D scanner, in order to create a full point cloud of the environment at different time instances, and they aligned these point clouds of these different stages with respect to each other. And then to ensure or to generate the actual data set for the users of the data set, what the team did was simulating positions of the laser scanner. So basically simulating that this sensor was placed somewhere in the construction site and basically generating what the sensor would have seen, specifically a point cloud. So basically they're slicing these large point clouds into smaller point clouds. And additionally, what they're providing is a post-graph representation. So that basically means that the nodes of the post-graph are referring to the point clouds, while the edges refer to the rigid body transforms to close point clouds. And yeah, basically they're also providing this in their data set. And the goal then for the participants is to find the set of edges which minimizes the global root mean square error for the whole construction site. Now, compared to last year's challenge, in order to ensure a hidden test set, the full data set was regenerated by randomly sampling all of these locations and creating basically a completely new data set, resulting in 4,600 new locations. Additionally, the camera height was randomized to be within 1.2 to 1.9 meters. And as a consequence, of course, new postgraphs were spawned with this time with different sizes of 10, 20, 40, and 80 nodes in order to enable multi-way registration of different scales. And this time also there were guarantees made for the postgraphs, specifically that each node had a degree of at least 2. So that basically means that each point cloud had at least an overlap with 2 other point clouds in the data set, where this overlap between 2 point clouds was at least 10%. And globally, across the average overlap across all the point clouds was at least 30%. And that resulted in about 200 postgraphs per building. Now, the data speed basically remained the same with like last year, where 3 construction sites were used for training, 1 for validation, and 2 remained hidden on the evaluation server as as a test set. And again, the metric which determined the winner was who scores the best global root mean square error here. Now, these are more like specifically not only the global RMSE, but also the average rotation and translation error, but I'm not going into too much details here. But rather, we are now announcing who are actually the winners of this year's challenge. Starting off with the second place, where Xuan Yu Yang, Ling Ji Li, Zhengbao Wang, and the Associate Professor Simon Quan, as well as Associate Professor Jiaqui Yang from the Northwestern Polytechnical University, as well as Chang'an University, scored the second place. Applause. Now, unfortunately, nobody is present physically, but we will see a presentation via Zoom in any moment from them. And for the first place was scored by Daebom Kim, Seng-Ya Lee, Seo-Yong Yang, and Jai Kong from the Korea Advanced Institute of Science and Technology. Congratulations. So please come up to the stage for the official handover. Okay. Yeah. Very exactly. Wonderful. Thank you. Now, maybe a short notice on what is next for the Nothing Stands Still Challenge. So the idea for next year is to additionally add semantic information to the data sets in order to unlock more computer vision and robotics tasks. But if you have any other ideas, please give feedback to the challenge team on this email, which you also find on the internet, in order to influence what will be happening next year. And thanks a lot for the attention. And with that being said, I'm now handing over the stage to the 2 winning teams. So I would say we start off with the second place and then proceed with the first place for the presentation.